All right. Hi, everyone who is joining. We are super excited to see all of the people in the waiting room. Oh, okay. Maybe for those zooming in from outside of the UK, you can write in the chat where you're zooming in from. I would really love to know. Very curious. I will start to make it less awkward. Oh, Edinburgh, hi, welcome.
Hey, welcome.
Nijmegen. Actually, I'm not sure how to pronounce Nijmegen, so I'm sorry to all Dutch people who are present. Oh, that was good. I'm glad. Oh, Hamburg. I love Hamburg. Yes, represent. So we're just still letting in some folks, and then we shall get started in a second. Super nice to see all of you here. Oh, Manchester, Moscow. I think that's definitely the most exotic location that we've had so far. Steph, correct me if I'm wrong.
Yeah, definitely. And
Welcome,
thanks everyone for having your mics on mute to start. That's great. Thank you very much.
So I think I will get started with explaining a little bit of the housekeeping procedures, and then we'll just let folks join as they enter the waiting room, but let's kick off. So welcome everyone to the Glasgow Reproducibility meeting. Today we welcome a very special guest, and Steph and I are super, super excited.
We are.
And yeah, I always explain a little bit at the beginning how we run this meeting for all of the newcomers. Basically, Amy is going to discuss the paper that she picked for us to read today. And you can also, during Amy's talk already, ask questions in the chat as they come up. Yeah, exactly. Hi, Helena. Also nice to see you. You can just post your questions in the chat, and then one of the hosts who's monitoring will interrupt Amy, and then your question will be asked. If you prefer to ask your question yourself, you can do that in the informal Q&A at the end of the meeting. And during the talk, we would ask everyone to turn off the microphones. And we also want to make you aware that we are recording the talk portion, which is just the first 20 to 30 minutes. So if you have some more like controversial questions, or I don't know, you want to have your privacy protected a bit more, you can ask your questions at the end of when we have the Q&A, which that will work. Sorry, I always get so nervous and so excited when so many people are joining us. So that's why I'm not making a lot of sense right now. But I want to start by welcoming Dr. Amy Orben, who is a research fellow at Emmanuel College, University of Cambridge, and a research fellow at the MRC Cognition and Behavior and Brain Sciences Unit. Amy has obtained her doctor in philosophy and experimental psychology last year and was awarded by the British Psychological Society the award for outstanding doctoral research for her thesis, Teens, Screens, and Wellbeing, which actually is online, and I can recommend you to look it up. It's absolutely amazing. And she is, of course, also the founder of the very reproducibility that we are all a part of today. So let's welcome Amy with a virtual applause.
Thank you, and thank you so much for organizing. I'm quite honored to be kind of the last one of this series. I know how much effort it takes, especially in a pandemic, and kind of even if it's just a couple of hours a week, that extra energy above and beyond kind of normal day-to-day academic business can be really challenging. So yeah, thank you for organizing. My talk I titled A Hitchhiker's Guide to the Multiverse, and it's kind of a culmination of, I guess, my PhD, where I used these methods in every single one of my chapters, except the kind of introduction. But then also a lot of discussions that have gone on, both, I think, me personally with different people in a kind of learning process around what these methods might actually be, what are the pros and cons, and then a bit more formalize the paper that is now in press at AM and PPS about kind of thinking a bit more strategically about when a multiverse makes sense and what you need to think about when implementing it. And so a lot of my talk will be very basic, talking about what kind of multiverse methods are, and also how I got to use them in my PhD. But I hope that in the discussion and in later sections of my talk, I can introduce you a bit to, I guess, my learning process in using these methods and some of the criticisms that I think are kind of should be taken very seriously about these methods as well. So yeah, so I put loads of planets all over my slides because it's the Hitchhiker's Guide to the Multiverse. So this is a planet multiverse. I think when I made these slides, I was way more excited. Not more excited, I was way funnier than I am now. It was on a Friday afternoon and now it's a Monday, almost morning. So, but yeah, so this will be reflections of a fellow traveler on kind of the guide to the multiverse. I'll first talk about the origin of the planet multiverse, why multiverses exist, why they're important. 2, why I found the planet multiverse, kind of what in my PhD made me want to use these methods. 3, what I did. So what did I do during kind of using the multiverse? And that will probably be quite short depending on time. And then 4, I think most importantly, some things that I've learned and things I would do better next time. So let's go to number 1. So some of you might have seen this slide or heard a similar talk. Kate Button has a talk about analytical flexibility that she introduces with this story, and I've just taken it and adapted it into my talks about the multiverse because I think it's really a great kind of way to start thinking about analytical flexibility. So in the UK, there was a TV show a couple of years ago called Derren Brown, The System. And Derren Brown was a guy who you were told could predict the future. He has this very specific skill and he could predict which horses win on a certain horse race. And the TV show follows this woman that he is advising with his kind of supernatural powers. And he tells her which horse to bet on these horse races. And he tells her kind of the first horse to bet on one race, and she wins. The horse wins, and so she starts trusting him a bit more. She puts a bit more money on the next horse. He tells her which horse will win on that race, and she wins again. So naturally, she starts trusting Derren Brown more and more, becoming more convinced of this power to see into the future. So up to, I think in the 5th race, she actually puts a huge amount of money onto the horse he tells her will win. So there we have kind of accumulation of evidence towards this story, the story that Derren Brown has supernatural powers, which naturally can't really be true. We know that precognition and kind of predicting the future is probably not true, it's not possible. However, in this television show, there wasn't any trickery. You know, there wasn't any kind of cutting and pasting or acting. Everything was true. Yet while there was a system that guaranteed that she won and won again and won again, it wasn't the system she thought it was. And it wasn't a system we as the audience thought it was, aka that Derren Brown could predict the future. And what the system actually was is that instead of just one woman being in the TV show, actually the TV show had started following 7,776 people. And Derren Brown randomly kind of guessed a horse that would win for each one of them. And actually, because there was kind of limited amount of horses in the race, a couple thousand people actually won because the randomly allocated horse actually won that horse race. And only those people came on to kind of the 2nd race. So the rest were just forgotten about, they were excluded from the television show, and then the 1,296 kind of people who'd won kind of bet on the right horse in the first race were again told that Derren Brown had predicted that another horse would win in the next race. Again, only a fraction also had that race like being won. And so then we had 216 race 2 winners, again randomly allocated a horse. Out of these, 36 winners from race 3 were randomly allocated a horse again for race 4. And then in race 5, there were actually only 6 who had consistently won in terms of Derren Brown's predictions. And so at the end, we only had 1 out of 7,776 who had kind of, Derren Brown had just randomly predicted 5 consecutive wins. So now we as an audience, and if she would have known this story, she would have interpreted the evidence very differently. You know, it's just mathematical probability. It's just luck. And so if we know all these different options that had kind of those 7,776 people who were also in the experiment, we would have come to a very different conclusion. So in a way, you could see it again as a garden forking path or a winning streak. So the one kind of person who won all 5 races. And in a similar way, this can happen when we analyze our data. So when we analyze our data, we need to make a lot of different decisions, whether that's, you know, we be in psychology or in biostatistics or in chemistry. There are a lot of, naturally, the types of data analysis choices vary, but we still need to make a huge amount of them. For example, how do we define our outcome variable? You know, do we transform that outcome variable? What covariates do we include? What is another one? Maybe what's the predictor? What's the population we're looking at? Who are you excluding as outliers? These are all a huge amount of analytical decisions that could branch out into, again, such a path of all these different options. And if we only report the one streak that worked, people might get the wrong idea. We might be communicating, for example, that Derren Brown has supernatural powers, while actually if we would report all the other analytical pathways that maybe didn't quite work out, we would have come up to a very different conclusion. So this is this kind of idea of analytical choices being this garden of working paths where certain choices can create different types of outcomes have been quite popular for quite a long time. So Andrew Gelman talked about them in terms of p-hacking. So for example, you might have, you might look at what outliers to exclude, and you might exclude 2, and you see that actually your p-value gets kind of less significant. And so you actually go and you actually exclude 5, but you could have also excluded 0. There's no real kind of theoretical reason to have chosen either one of those. You only chose because of the p-value. And then you might go down to the next one where you need to choose whether you log transform an outcome variable. And again, you might test. You might try whether what happens to your result. And if your result goes into the opposite direction you're predicting, you might say, oh, log transforming doesn't really make any sense anyways, so I'll just keep it as it is. And so over time, you'll go down this garden of working paths, and you might get a p-value of under 0.05. But if you look at all the other pathways through this garden of working paths, they might all come up differently. And so by only reporting the pathway that you took, you might be biasing the strength of your evidence, for example. And he said in this quote that research degrees of freedom, which is another name for this analytical flexibility, do not feel like degrees of freedom because conditional on the data, each choice appears to be deterministic. So what he's saying here is that once you've gone down this garden of working paths and you maybe reached your p-value of under 0.05, you might look back and say, naturally, I didn't transform my outcome variable. Naturally, I excluded 2 outliers because that makes sense. You know, I have a reason to do it, but you're only making this kind of up after you did the data. And it's very natural for us to see the way we analyze the data as being the kind of way we should have done it all along. But if our results would have been slightly different, we might have well excluded no outliers and log transformed our outcome variable, and we would be just as confident in how we analyzed our data. So there's actual experimental proof that if you are flexible in your analyses, if you kind of don't, if you're flexible enough, you can actually make impossible things happen. So it's kind of like the TV show, but in real life. And this is one of my favorite papers. If you've not read it, please do. It's absolutely brilliant, by Simonson, Nelson, and Simonson in 2011, where they showed that if you have, it says it all in the title, undisclosed flexibility in data collection and analysis allows presenting anything as significant. So they have a couple of different points of analytical flexibility, and they actually showed that they had an experiment where a certain group of participants got younger by listening to a certain song versus a control group. And naturally, you cannot just become younger when listening to a certain song. But they showed that because they were very flexible in how they analyzed the data, they could get to that conclusion. And I think ideas around data analysis have now strengthened this flexibility of data analysis. I don't think the field now doesn't see statistics anymore as a microscope. You hold to the data and you can see what's in the data. Instead, we're starting to see that statistics is just is a powerful tool that can actually change what we see in the data and how we do it. In the many analyst papers in AMPPS and psychology, for example, they had many different teams of statisticians analyze the same data set with the same research question. And then they found that each team analyzed it slightly differently and also came up with different results. So again, we know that statistics isn't kind of a clear one path you're going to take from your data to the final product. Even statisticians who are trained in this process of data analysis make different choices. And this is not just in kind of general psychology. We've seen this in fMRI. This is a paper from Ross Poldrack showing that there are about 70,000 different ways of cleaning fMRI data. And just recently, a many analyst fMRI version of the study got published in Nature showing similar kind of levels of flexibility. And you see that there are multiple different many analyst projects now going on in, for example, ecology, in epidemiology, in fMRI. And I normally had a slide here about genetics, but I must have deleted this. But yeah, there's also work in genetics on this. So what can we do to guard against this garden of forking paths, to make sure that the one pathway we report is actually an accurate reflection of the strength of evidence that we have? Well, there are multiple different ways people have thought about. The first is we should just be transparent. You know, in 2011, Simonson said, we should just say, you know, what our conditions were and what observations we eliminated and the covariates, and we just need to be transparent and that will fix it. But later, Felix Schönbrot in Munich created this 21-word solution, a sentence that you can put, kind of a journal can mandate people put in their papers, which says, we report how we determined our sample size, all data exclusions if any, all manipulations and all measures in the study. And that way it's kind of making that transparency more concrete, because if I wasn't transparent and I add this sentence in my paper, it's actually an error of commission. You know, I'm actively lying by not being transparent, rather just not saying anything. But over time, there's been some more kind of successful solutions. The one of them that probably most people know on this call is pre-registration. Pre-registration, in a way, solves this garden of forking paths by kind of, as a researcher, when I pre-register, I tie my hands beforehand. I say, I'm going to take exactly this pathway from data to final analysis. For example, you know, on this slide, it's this red pathway. You know, I'm going to exclude outliers if they're in the X percentile. I'm going to log transform if this test comes out positive, or I'm going to log transform any kind of income variable, for example, because I think that's theoretically important. And because I'm not making these analytical decisions while looking at the data, there's no bias in which pathway I choose. You know, all these pathways might still lead to different outcomes in my study, but I don't know which ones will be the kind of significant outcomes beforehand. So I'm kind of randomly choosing, or kind of as an informed researcher, choosing which pathway I think is best before actually knowing which one is best for my career, because that one shows, you know, that my intervention worked. So it's quite a simple method, you know, it's very straightforward and it's very powerful. The only negative that came out at times is that you need to prove that you've not seen the data. Like, because naturally, once I've seen the data, I might be biased towards certain analytical decisions because I know what the data looks like. And with secondary data analysis, that can sometimes be difficult. But there is now a paper which looks at pre-registering secondary data. So do have a look at that if you're interested. I don't need to talk about how pre-registration registered reports are really popular. So let's look at solution 2. So solution 2 is the multiverse. So we kind of put pre-registration on its head, and we say, well, why don't, instead of pre-registering one pathway, you know, and we already have the data, why don't we run all kind of analytically robust ways of analyzing the data? You know, why do we need to choose one? We just take this garden of working paths here and we run every possible way we could have analyzed the data. And then we just report all of them. And that's kind of the basic of Multiverse, is saying there are many ways to analyze the data, and there are probably many ways which are equally good. And if we run all of these equally good ways, we might have a more kind of transparent and better understanding of the data. So they're kind of similar but very different, pre-registration versus Multiverse. So just a quick, like, this will be a very quick and kind of idea of how you run a multiverse conceptually, is 3 different steps. So you first need to identify all these analytical pathways you could go down. So in a way, you identify what analytical choices you need to make. For example, how, you know, outlier exclusion, transformation, how I define my outcome variable, what population I look at. And for each one of these choices, I could probably make multiple different analytical choices. For example, I exclude outliers because of a percentage, or I will just exclude the 2 most extreme ones, or I don't exclude anything. And so for each of these choices, you might have multiple ways. In multiple ways, you could have made that choice. And so you write all of those down, more or less. And then you get to step 2, where you run a script which kind of goes through every single possible combination of all these choices, runs the analysis, and kind of takes the result and puts it into a table. And then, yeah, sorry, Anna, you can go ahead.
Yeah, sorry, I'm just asking a question on behalf of Helena, who I think the question was about the previous slide. She says, for me as an ECR, especially when I was starting out in my PhD, doing a pre-registration seemed crazy daunting. I tried, and my pre-registration was definitely not perfect, and I'm still trying to improve as I go on. I was wondering if you could comment on starting out with open science principles, and if you have any tips for this time.
Yeah, I think the pre-registrations are always really hard. And I think the first one will always be a mess, kind of, at least I think for most people. And so I think it's quite hard sometimes that pre-registration is often people's first experience with open science. At least if we often define open science with quite high kind of stringent benchmarks, you know, not just, you know, making things a bit more open. A lot of people believe that pre-registration is kind of the epitome of open science, and at least kind of in the first step when they come into that field. And so it's really difficult, because it's really difficult to get pre-registration right. What I will argue in this talk is that it doesn't mean that, you know, I think it's still really important to do a pre-registration if you can do a pre-registration. And like, I don't think Multiverse is a solution if a pre-registration is too hard, because I think Multiverse makes everything a lot more complicated. So yeah, and I'll argue more about that later. But I'm happy
Yeah,
to have a
Helena,
discussion later.
that sounds good. Helena says, thanks a lot, Amy.
Cool.
Yeah, thank you.
And I think it's in a way we need to think about how can we make pre-registrations easier. Kind of naturally, if you educate people earlier, for example, in their undergrad project, they'll make those mistakes earlier, and it's not like your important PhD study number one. Anyways, so back to the multiverse, or specification curve analysis, whatever. There are multiple names you can call it. You've now run all these possible ways you could analyze the data, and then you can do statistical inferences with it if you want. It's quite complicated, so I won't go into a lot of detail. But if somebody wants me to, I'll happily answer that question after the talk. But you can do bootstraps, or you can just graph them and kind of look at them descriptively. But all of a sudden, you might have 100 different results to your study, and you need to then do something with that. So just as an example of a multiverse, to give you a better understanding, I want to talk about the study that really originated at least the idea of a specification curve analysis, which is Simonson and colleagues wrote about. And they wrote about this study. So in 2016, there was a PNAS paper that said that female hurricanes are deadlier than male hurricanes, study says. And I remember reading this as like a layperson being like, wow, because they said more or less in America, hurricanes are named female or male names, kind of they alternate. And they said that when a hurricane was named a female name, people would underestimate its strength. Naturally, in a way, this is quite a kind of funny study, but naturally also has real public health consequences. You know, if this is really true, then we should just name everyone, you know, Zeus or like some crazy, like powerful name. But over time at PNAS, these letters started coming in where people would reanalyze the data and found that they didn't find that female hurricanes were more deadly. So for example, this was the first letter saying, are female hurricanes really deadlier than male hurricanes? They'd gone into the data and they'd had a look around. Then there was another paper saying that population matters when modeling hurricane fatalities. So they'd looked at the population category and said that actually if you define it differently, you don't find it anymore. The letters became more direct. Statistics show no evidence of gender bias in the public's hurricane preparedness. And lastly, female hurricanes are not deadlier than male hurricanes. So if we think about the garden of forking paths again, we have kind of probably a garden of many, many paths. And one of these paths was reported and they found that female hurricanes were more deadly. And now 4 teams have gone in, analyzed 4 different paths and said that they're not. Simonson and colleagues, when thinking about the multiverse at first, said that actually there must be a better way to look at the strength of evidence. And the better way is not just to run 4 different analyses, but to run all theoretically defensible analyses that could have been run. And to do that, they set up this multiverse. They had 5 decisions that kind of analysts needed to make, which covariates to include, which storms to analyze, how you operationalize femininity, etc. And each of those had maybe 2 to 3 or 4 options. They said original or alternative specifications. So for example, if femininity, in the original study, femininity was rated by coders on a 0 to 10 scale, while they said, you know, you could have easily also categorized hurricanes as male or female on a dichotomous scale. And so by kind of noting down all these different analytical choices, they then ran all possible analytical pathways for that study. This graph is very complicated, but I'll go through it bit by bit. I know I'm running a bit behind time as I expected, so I'm going to do this quite quickly. But if we just look at the top part of this graph, the graph has all this blue, light blue line is actually not a line. It's loads of little dots. You can kind of see it up here. And these are all different analyses. And here are the extra deaths. So if it's underneath the 0 axis, then male hurricanes are more deadly. And if it's above, female hurricanes are more deadly. So just looking at these analyses, we see that, you know, maybe about 20 of these 300 selected analyses show that male hurricanes more deadly. Oh, it says 20 on here. Oops. 20, while a lot more showed that female hurricanes were more deadly. But only these black dots were the only ones which were statistically significant. So here they say 37 out of 1,728. Here they only displayed 300 for this visualization to make it easier. But you can see that only about 7 of these 300 analyses were statistically significant. And the big black dot is the one that was reported in the paper. So like in the Derren Brown study, you know, if we just see this, we think that is really strong evidence. But now if we see the whole graph, we can see that the data is tending towards female hurricanes to be more deadly. However, there are very few analyses that are actually statistically significant. So if you randomly selected one of the PAWs here, one of these specifications, it's very unlikely you would have landed on a black dot. So kind of your publishable PNAS study. So that shows that there probably was some sort of flexibility involved, if it's kind of conscious p-hacking or more unconscious biases in data analysis. We don't know. But yeah, so this is kind of the strength of a specification curve analysis or a multiverse, is that you show all these different results. And these kind of graphs at the bottom tell you which analytical choice led to what result. So it also helps you explore kind of which choice might bias my results to be more negative or more positive, for example. This is not kind of the first idea. Naturally, Sarah Stegan had written about the multiverse and, you know, has a way better name to specification curve analysis way earlier. And in a similar way, you know, these are all similar ideas of taking this garden of forking paths and displaying it on a kind of in an analytical way. So there are multiple papers in this area to look at, and the paper that I asked kind of people to read also goes into some other kind of names this idea has gone under. You know, in genetics here, there's a paper said, I just ran 1,000 analyses. So even without putting a name to it, people have been doing this. And the same with the CART paper in fMRI. Here they ran 6,900 unique analysis pipelines and 34,000 significant maps. So that's kind of the origin, and I will be very quick for the next two sections. It's the origin of the Pi multiverse. I hope it makes a bit more sense what the multiverse is actually about, what the kind of analysis is in a sort of intuitive sense. I just want to discuss about how I found the multiverse and why I decided to start using it. Was very much down to my area. It's about smartphones, and there's a lot of kind of crazy debate going on, and people are quite passionate about whether smartphones harm or help. And this kind of Atlantic article in 2017 wrote about that kind of smartphones are causing people to be depressed, especially teenagers, and that this is destroying a generation. And the article was, I will go on. The article was based on this paper, which again used a large-scale accessible data set to show that there is a negative correlation between screen time of adolescents and depressive outcomes. So I didn't have a lot to do with my PhD then. I wasn't very happy with what I was doing. So I started looking into this open data set. And this is what I found. So kind of social media use on the x-axis, depressive symptoms on the y-axis. And you can see like the blue line is a regression line and it's slightly upwards. So, and that is a positive link between social media use and depressive symptoms. Whether that is destroying a generation is kind of the next question. But this showed that in large data sets, really small correlations can become statistically significant. Furthermore, these large data sets are really complicated. They're run by governments, they're run with sociologists and economists and psychologists and political scientists and epidemiologists, and everybody wants to have questions in there because a lot of money is needed to kind of collect these very large data sets that are openly available. For example, in the data set that was analyzed, there were 12 different questions which pertain to well-being in adolescents, coming from 2 different questionnaires, the green one and the blue one. And I kind of did a little review of different studies that had said to look at well-being and which questions they used from that study. And people had selectively chosen what questions. They didn't really stick to the questionnaires. They just chose the questions, I guess, which we were interested in or which worked. So for example, here some studies use 4 items of this kind of: life is meaningless, I enjoy life as much as anyone. But then some added other measures or deleted one of the measures or used kind of other. So what I wanted to say is that there's a lot of flexibility in how this data was used as well. So you don't only have kind of small effects becoming significant really, really easily. You also have a huge expansion of this garden of working paths, because there's a huge amount of decisions people can make in these really large data sets and how they analyze them and what measures they use, for example. So I say that is data that is too big to fail. You know, it's just, if you analyze it flexibly, it will always work. So that's kind of why I started doing the multiverse, and that was my first big multiverse paper, was actually going in and trying to show this analytical flexibility in these papers. Number 3 is what I did. I just added a graduation photo, just short, kind of to quickly summarize. I'm happy to go into this in more detail. Mine ended up being 3 studies to kind of using multiverse methods. The first one was kind of multiverse on steroids. So going and doing a multiverse of millions of different analyses to show this analytical flexibility in large data sets. So for example, with the well-being measure, I could just, if you can just choose whatever questions you want out of 20 questions, there are thousands of different ways you could have defined well-being, because you had 20 different questions and you could just choose which combination you want. So I kind of took the multiverse to the extreme and ran every single possible way you could have analyzed the data. Whether that was good or not, we can discuss. The second, I merged it with pre-registration. And then in the third, I used multiverse as a sort of background, almost like a error bar. So I chose one analysis path that I thought was best, but then I ran a couple, I think it was about 20 other analyses that I thought was probably just as good. And I showed them in the background as kind of jitter to show the difference. Okay, in the last 2 minutes, I will discuss some things that I've learned and things I would do better next time. And this is to do with the paper that we read. So I'm just going to actually quote the paper here. The central notion of these methods, so of multiverse, is that the alternatives included in the multiverse are arbitrary or equally reasonable. However, there is little guidance or consensus on how to evaluate arbitrariness, and virtually no consideration of the potential pitfalls of multiverse-style methods. What are the implications if some of the choices regarded as arbitrary are in fact not? We feel that researchers have started traveling across the multiverse without a map, and often with surprisingly little awareness of the dangers that lurk out there. So what this paper says is that you should really only run a multiverse if all the different analyses that you're running are equally good. But how do we know whether they're equally good? So for example, my first paper, I naturally ran certain analyses that weren't equally as good because I ran millions of them to kind of show this analytical flexibility, which I think was, and I had this discussion with the authors, I thought was merited at that time, but isn't merited, for example, if I want to use it to make an analytical statement. And so I think I learned a lot about that. A multiverse, you really need to think about each single analysis you put in and if they're actually equivalent. Are they all equally as good? And maybe, you know, that probably means your multiverse if it exists, might only be 10 or 20 different types of analysis if you're really stringent in what you put in there. So this is the paper. And I just wanted to finish with 3 points the paper raises that you need to think about if you run a multiverse. So the first is that, for example, what I did in my PhD was to show this kind of selection of questions from the questionnaires, I ran one with every single possible combination of well-being items, which probably means that my analyses weren't equivalent because the measurements were different. So I should have probably ran one instead with just the the measures that were actually validated instead of, oh, Anna, go ahead.
Yeah, I'm just interrupting because Jack asked a question exactly on this subject. So Jack writes, if all the analyses aren't equally good, would it make sense to weight the importance of the evidence from different pathways by the prior beliefs and appropriateness of each pathway? Could you quantify it via simulations looking at type 1 and type 2 error rates?
I think there's definitely a big space to look into that. So Katie Drax, God, I forgot like the name of key colleague of mine. Katie Drax has been doing a really cool project where they're kind of mixing many analysts with multiverse. So they have many analysts kind of analyzing a data set with the same research question, and then they tally up all the different choices they make and the popularity of certain choices, and then they want to weight them in the multiverse. So they kind of use the many analysts to extract the weightings for the multiverse. Naturally, you could also weight the multiverse in terms of simulation or in terms of asking people to judge kind of the analytical choices outright, you know, just give experts in the field different choices. I think there is a lot you can do. But yeah, it's still kind of work in progress for a lot of those, yeah. So the one kind of non-equivalence of analytical choices is important to think about measurement. It's important to think about the effect. So that's about causality. So for example, if I add gender in as a control variable in a regression, the kind of effect that I'm estimating is very different to if I add in 36 other covariates. You know, the effect might be kind of a completely different effect I'm actually estimating. And so thinking about causality and thinking about DAGs, directed acyclic graphs, that Julia Aurora wrote a really great primer on, is really important as well, because if you do different analyses, you might be actually estimating very different effects. And so putting them in the same multiverse doesn't make any sense. And the third is power non-equivalence. So for example, in one of my multiverse, one of the analyses had about 1,000 participants, while another analysis had about 15,000 participants. And so because the power imbalance, again, it might be that they're not equivalent analyses. And maybe I should just have run the one with the most kind of at least analyses with a similar level of power. So these are kind of the 3 points this paper raises in terms of kind of things to think about running a multiverse. And I hope we can discuss about it more. So I think my reflections to at least give us 15 minutes of discussion is, don't just do it because it's cool, do it because it's the best method for the job. So multiverse, and this was like my whole PhD viva was about this. So I think a multiverse is a really powerful tool in very specific circumstances. And I think I wanted to give this talk because I've started having a lot of conversations where people just say like, oh yeah, I love a multiverse. I'm just gonna add it to my project because it's so cool. And I'm always like, well, a multiverse is a lot of effort, and it's a lot of effort to do right. And I think for me, it took weeks and weeks and weeks. And I think I didn't do it 100% properly. Probably, you know, mainly because I didn't know how at the time. I was just teaching myself R, you know, I was in the middle of a PhD. But I think multiverse are really great as an exploratory tool, as maybe a tool to look at analytical flexibility, as a tool to look at how little changes in your analyses might have made a difference. They're not, like if you can't pre-register, for example, that's a much easier way to solve the problem of analytical flexibility, especially if you're doing experiments. For me, it makes a lot of sense just to stick with pre-registration. But yeah, I think there's a lot of nuance of whether a multiverse works. Then 2, don't start traveling without having a big think about what analyses you want to include and why. Think about non-equivalence. I know it's really hard, but better to tone down the multiverse and make sure that each of the analyses makes sense rather than to run a lot more. And 3, think about what you will do when you arrive in terms of results communication. It's really hard to communicate if you have 100 results. And maybe if you're in a project where you really want to communicate results properly, you might want to go with, and I think I put this in here, this was the last multiverse I ran. And this was the one where I said we kind of had a preferred analysis and then we added other multiverse analyses in the background. This is kind of what it looked like, is that the black and white dots were the kind of preferred specification, and you could pre-register that, for example. You could say, this is the way I think the analysis works best, but then there might be 20 other ways that could be just as good. And I'll analyze them, but I'll put them in the background, almost like error bars in the back, and these were little dots. So I think, think a lot about them. But yeah, thank you. Sorry that I overran. I had a lot of information to cover. But yeah, I'd love any questions, criticisms, ideas, yeah, whatever. And I'll stop my slides